Hello and welcome to Physics Problems One by One. So here is a problem. As always, read it, maybe once, maybe twice, and then pause the video and try to solve it yourself. Today's part 3. The same problem about the body that free falling with acceleration g covers distance L equal 100 meter, and then they want us to know how much it covers in the 1 second, and we got the answer. And if it's 1 meter, how much time required to cover this 1 meter, and we got the answer. We also received what is the total time. And then they were asking us for the last meter, how much time it will take to cover last meter. And then they were asking us 1 second, if we're going for 1 second, how much distance we cover in the last second. And we obtained all those numbers, and everything is fine with this. Just want to compare these numbers to get you a better sense of what's going on. So let's draw horizontally. Because it's one-dimensional, I can tilt it the way I want it, and I can say that this is my starting point, and this distance is L, and it is 100 meters, right? And I immediately can put the time, we figured it out, it's around 4.5 seconds time-wise, right? Now, the distances, we have here 5 meter. 5 meter would be 10, 10, 10, it would be very small. It would be something like this, it's 4.9 meter. 4.9 meter. Oh, we also have distance 1 meter. Yes, even smaller. And it is 1 meter. Now let me draw it a little bit better because, so this is 1 meter. And this is 4.9, and I will put here meters, right? And this would be seconds. And so 1 meter we cover in a half of a second, 0.45 to be precise. And 4.9 meters we cover in 1 second. Right? And then we have this total distance, 4.5 seconds, and then last meter. So last meter would be somewhere here, and last meter, this would be accordingly last meter, so it would be let's put it here, 99, right? And accordingly this time, so this would be 1 meter, and this time would be 0.25, right? And then if this is 1 second, 1 second would be very long comparable to this 0.025. And then this last second, the distance would be 40. So 100 minus 40, it would be somewhere here, 60. Okay? So this would be 1 second from here to here, and we will cover 40 meters. So this distance would be 40. And 60 meters from here. So what's going on? In the beginning, when we spend half a second, we will fall only 1 meter. The body will cover only 1 meter. Half a second. Now, when we go quite a bit of a distance, 60 meters, we double this 1 second, double this to 1 second, and we cover 40 meters. Why? Because by this time we have we gain a lot of speed. So we're traveling with a lot of speed, and during this 1 second we cover 40 meters. Look here in the beginning, we cover 1 second and we cover 5 meters. from here, the same 1 second, we cover 40 meters because we accelerated quite a bit. In the beginning, it's also very uneven. 0.5 versus 1 second, it's practically double. But the distance is 5 times more. And this is all related to the fact that if this is time and this is coordinate, it goes like this. It's nothing like we have a constant speed like before. In the same time we cover some distance. No. In this time the distance that we cover is very small. In the same time, like this, but from here to here, the distance would be this. And this is what those numbers show. So once again, in the first half a second, only 1 meter. In the first 1 second, 5 meters. In total, 4.5 seconds. And first 3.5 seconds we cover 60 meters. And once last second we cover 40 meters. So if I will draw this graph here with those numbers, and I will put 1 second here, half second here, and I will put 2 seconds, 3 seconds, 4 seconds, 4.5 seconds. 4.5 seconds would be my total time, and I will cover 100. This would be 100. So t, x, and this would be 100. So this would be the point when in total time, 4.5 seconds, I covered 100 meters. Now here in the beginning, 0.45 seconds, I cover 1/100th of this. It's just negligibly small. You cannot even put it at scale here. Now, this is 0.5. At 1, it would be already 5 meters. It would be something. You barely can see it, but you can see 5% of this distance, 5 meters from 100. Okay. Now, 60 meters is more than the half. It's somewhere here. It would be covered in first 3.5 seconds. 3.5 seconds, 1, 2, 3, somewhere here. So first 3.5 seconds, we will come to here. Somewhere here. And this would be 60 meters. And then the last second, from 3.5 to 4.5, we will come here. So this is how parabola will look. It looks like a straight line, but nothing of a sort. Now, if I compare the same distance here, which is 1 meter, and it would be something like this, and this would be this distance, it would be so much closer to this final time, it will take only 0.025, whereas this was 0.5, so it would be 20 times this distance, this time, sorry, is 20 times of this small interval. So it's very difficult to draw it with a chalk on the chalkboard, but it would be even difficult to draw it on the paper with all the lines. It would be more useful maybe to draw on a screen of computer with pixels and pixelations and everything precise. So you can try to do it maybe yourself if you're interested. But the idea here is that this is uneven motion. Acceleration is constant, speed is constantly growing, and that's why everything is uneven. And I hope this was useful for you, those 3 parts where you used formulas for first meter, first second, last meter, last second, and compare the numbers. It was useful for your understanding what it is and how uneven is the one-dimensional movement with a constant acceleration. Constant speed, everything is even. Constant acceleration, not so much. Thank you very much. Subscribe, bell, like, question, problem, comment, and I'll see you next time. Thank you.